Okay, so in the earlier 20th century, right about the time that the Bohr model was proposed, Gilbert Lewis was a chemist who introduced a very convenient and really simple model for covalent bonding. That is, for the formation of bonds holding atoms together, and generally these correspond to non-metal atoms primarily, though some metal atoms are also described by this model. Anyway, in this model, he suggested that covalent bonds are formed by the sharing of pairs of electrons. Okay, and he introduced this idea called Lewis diagrams, or sometimes called Lewis dot structures, to represent a model for these covalent bonding involving both bonding electrons, that is pairs of bonding electrons, as well as pairs of non-bonding electrons, that are called lone pairs of electrons. Okay, so in these Lewis structures, he basically represents the valence electrons for all elements, for all atoms, by dots. Okay, and so if we look at the symbols for individual atoms, the symbol of that element always represents the nucleus and the core electrons for that atoms, and then the valence electrons, those electrons that are on the outside that are responsible for the bonding, are represented simply by dots. So lithium in group 1 has a single valence electron, and it is represented like this, lithium with 1 dot. Then beryllium has 2 valence electrons. We write Be with 2 dots, and it doesn't really matter where we write these dots, but generally we're going to restrict ourselves to the left, the right, the bottom, and the top. So here boron with 3 electrons, carbon with 4. Now nitrogen, when we go to 5 electrons, notice that we've paired these two together. So we've stuck to these 4 sides, and then when we get to the 5th electron, we're going to pair this one up. Oxygen, we have 2 pairs and 2 unpaired. Then fluorine, 3 paired and 1 unpaired. Okay, and these Lewis symbols really introduce some insight into how these different nonmetals bind, and in particular the nonmetals. Okay, and so he introduced this idea of Lewis structures to represent the covalent bonding, that is, in terms of the sharing of pairs of electrons. And so he says that bonding within molecules, that is, the forces that hold atoms together to form molecules, always just involves the valence electrons. Okay, and so a chemical covalent bond results from the sharing of 2 of these valence electrons. Okay, we call these bonding pairs. And a Lewis structure is a simple representation of a molecule that only shows these valence electrons in either bonding pairs or non-bonding pairs. Okay. And so doing these Lewis structures, really there's a systematic approach. It's not just totally random trial and error here. Okay, so the first step, and here is a nice website, a link to a nice website here at the Purdue University that gives a nice tutorial of this topic. If your textbook is not helping you too much, or OWL, the instructions on OWL aren't helping you, this might be useful for you. So the first step is always to determine the total number of valence electrons, and that is just adding up all of the valence electrons from each of the individual atoms within that molecule. Okay, and we're going to do a couple simple examples here, and then I'll post another video with some more complicated examples. Okay, then we're going to use each of the symbols of our elements to write a skeleton structure. Okay, so we're going to figure out which atom is central and which atoms are on the periphery. Okay, or our terminal, and generally there will be some indication by the way that that the formulas are written that'll sort of tell us something about this. But we're not going to worry about how we determine that skeleton structure. For now, it's going to be fairly obvious. Okay, then we're going to, in the skeleton structure, each of the line that connects the atoms represents 2 valence electrons that are shared between these atoms. Okay, and then we're going to try to satisfy what is called the octet rule by distributing the remaining valence electrons as lone pairs. Okay, so we're going to basically say that each atom each non-hydrogen atom, that is, wants to achieve an electron configuration that is similar to a noble gas. And rather than gaining or losing electrons to do this, nonmetals like to share electrons to have their filled octet or their noble gas configuration. So this is easiest to understand if we do a few simple examples. Okay, so we're going to start with perhaps the easiest, and we're going to begin here with methane. So methane has a formula of CH4. So the valence electrons in methane are, we have 4 in carbon. Again, we can just look in our periodic table and the group number tells us the number of valence electrons. Carbon has 4. Each of those hydrogens has 1, and there's 4 of them. So we have 8 valence electrons in methane. And we're going to begin with, we will draw again what we call a skeleton structure by simply connecting all of the atoms with the lines. Now we need to figure out what is our central atom, and in this case it's really obvious because number one, carbon is written first. That's a good indication, but also hydrogen can never be a central atom. We'll find that hydrogen will never have more than 2 electrons associated with it, and that's because it's such a small atom. It only has those 1s orbital available for bonding, okay, in its ground state. Okay, so hydrogen will always be on the outside. It will always only have a single bond, never a double, triple, or triple bond, and it will never have lone pairs, except in the hydride anion, which we are not going to consider ever. Okay, so there's methane, and we have 2, 4, 6, 8 electrons that are associated with these carbons. So carbon has achieved its octet, and importantly, we have used all 8 of our electrons and no more. Okay, each hydrogen has just 1 bond, and that's how we will always see it. Okay, so let's do another simple example. Let's do ammonia. So ammonia, we're going to first count the valence electrons. All right, so nitrogen has 5. We're going to add that to the 3 hydrogens, 3 times 1. Again, in ammonia, we have 8 valence electrons. But now we've only got 4 atoms. So let's start with our skeleton structure. We draw lines connecting all of the atoms. Again, it doesn't really matter which side we draw these on, but it is important that nitrogen is central here because, again, hydrogen can never be central. So now we've got 3 bonds. We've got 2 electrons in this one, 2 in this one, and 2 in this one. So we've used up 6 of our 8 valence electrons, and we still have 2 valence electrons left. Okay, and so the next step is to accommodate all of the valence electrons as well as try to satisfy the octet rule for all non-hydrogen atoms. And this is easily done here for nitrogen, as we just put a lone pair right there on that nitrogen, and now nitrogen has 2, 4, 6, 8 valence electrons, and we're going to say that that's a good structure, okay, and that's a good representation of the ammonia molecule. And in fact, experimentally, we find that this simple model is completely consistent with the properties of ammonia. Okay, so our last very simple example here, let me see if I can make another page, is going to be the water molecule. Okay, so we have H2O. Okay, again, we start by counting valence electrons. So oxygen has 6 plus our 2 hydrogens. Again, we have 8 valence electrons, so we're keeping it simple here. So the first step is, again, to write our skeleton structure. Okay, here we have 2 and 4 electrons, so we still have 4 electrons to deal with, so we're going to write those as lone pairs. Okay, and we're going to put them on the oxygen and never on the hydrogens. So here now each hydrogen has a single bond. That's good. And this oxygen has 2, 4, 6, 8 electrons, and we will say we've done a good job. Okay, and again, this is a good representation of the water molecules, having 2 single bonds to each of the hydrogens and having 2 lone pair electrons, which are going to be really important for the properties of water. Okay, so we're going to stop here, and we're going to do another quick video introducing the idea of multiple bonds.